So long we have been looking at only one ROC curve. So we know how to draw the ROC curve. This is the data which Richard presented. So then how do you find the optimal cutoff value? Now we have said that it is not 1 point, it is 3 points, 2 minimum points, and there is a range of values in between. Now this is what we have discussed. Now the question is, when you want to evaluate 2 or more tests together and see which is doing better, then you need to draw more ROC curves and compare them. Okay, but you know what is the area under the curve? The area under the curve is if there is a perfect test with 100% sensitivity and 100% specificity, then you would get the area of 100% or 1. Otherwise, that the curve which gives the higher area is chosen as the best test. This is a small example to explain to you. There are 3 curves. The one is based on the ASAH. Other one is there is a score. Other one is WFNS scale. So they have 3 tools to measure the performance of whatever. And as you see here, when you look at this curve, this is coming closer to the diagonal line, and the area is this. This is 61%, very close to 50%, therefore it may not be very useful. The question must be asked is that the blue line and the green line, they are close to each other, so one could be taken as good as the other one. Okay, so when you look at the area, the question is about 85% versus 82%. So you have, now the question is, do you want to test and make sure that there is no difference or there is a difference? So that is what we are saying this as a comparison of ROC curves. So when you have more, this is like we say in analysis of variance, is there any difference across groups? So that gives you one p-value, doesn't mean anything to us. Yes, so there are 3 groups and there is a difference across groups, so what? So you wanted to explore where exactly the difference is. So therefore you would like to do pairwise comparison of these ROC curves. Okay. So this is the statistics which that your software generates. Now this is the number. Please tally these numbers whether what you have done is correct. And this is the disease positive and disease negative groups, and this is the area under the curves and standard error and C. Now this is looking at this confidence interval. Can you please tell me whether they are significant or not? Which is significant, which is not significant? So when I say significant, the area is significantly better than what? None of them is significant? Yes. So is it greater than 0.5, the area 50%? My curve should have an area better than 50%. So therefore you see here, this is the lower limit is close to 50%, but it has crossed 50%. So if your area under the curve range, 95% confidence limit, has 50% in between, then you will say it is not significant. You understand? When we explain that 50% is that tossing a coin. I don't want to do a test. So sensitivity is 50%, specificity is 50%. It's a useless test. So here, now the question is, of these 2, is it really better than the 82%? So that is what you need to ask. So therefore you would like to go for pairwise comparisons, and these are all various cutoff values. That at 50 cutoff value, this is your this is sensitivity and specificity. At this cutoff value for this scale, this is sensitivity and specificity, and this is this. So they are all different scales, and it gives you the best, the best cutoff values, and the sensitivity and specificity. Now you see here, it appears to be highly specific test, and this appears to be highly sensitive test. Okay, don't mechanically look at your AUC and try to choose. Now, when you look at the p-values, this is I'm comparing pairwise comparisons. This and this is statistically significant, and therefore this scale is better than the other one, because I remember that this one is the red color one, SAH, and so when you compare this one, now the question is this and this. So, and you see the p-value is this, and no difference between the two curves. So question is, you would call it as one is as good as the other one, or you would like to choose based on your sensitivity, specificity, and so on. So that is many times that yesterday we looked at how do we compare sensitivity in a ROC curve. Say for an example, you wanted to see whether this sensitivity is different from this sensitivity. So, or this sensitivity is different from this sensitivity, appears as though they are close to each other. So you can do the comparison within a curve, but if you want to compare the sensitivity across the curves, you should not be choosing a sensitivity alone. You have to choose the area under the curve, because that characterizes the performance of the curve. Okay, so that is something which we need to realize, that if you wanted to see this is a 73%, let's say this is 80%, you wanted to see 74% is different from 80%. Can I choose this or that? Then you can compare two sensitivities. Okay. But if you wanted to compare two ROC curves, one you pick up a sensitivity from here, sensitivity from there, then you should use the AUC to compare the performance of a curve. That is about the comparison of curves. Okay, this is what we have seen. The question which we have had, this is no difference. Any questions? Yes.
It's not about comparison. It's about AUC versus area under the curve. We know that it has to be more than 50. What is the acceptable number which it should be more? Like if you do a test and you get an AUC of more than 80. Is it okay, or you get something which is 75?
I'm not sure whether there is any cutoff value for that.
So even if we get a AUC of let's say 70 for a particular test, then we have to go for other tests, or
that I don't know, because she's saying what should be considered minimum clinically. Which I'm not sure whether I know about it. The earlier slide, there are two curves that are not significant to each other. So there's no difference between the two curves. So the question was, can we call one as good as the other one? Unfortunately, in statistics, if no difference, we don't conclude that they are equal enough. So therefore, so what you should do is, as it stands, there's no evidence to conclude that one is better than the other. That is how we take a decision. But if you have a priori question, the one is expected to be as good as the other one, non-inferior to the other one, because I know for sure test B is inferior in terms of sensitivity or specificity or AUC, but still I wanted to go for it because there are other benefits, cheaper and so on and so forth. So therefore you bring a non-inferiority concept into the comparison of ROC curve, so which we do in clinical trial. One treatment is non-inferior to other treatment and so on. Similar concept. So therefore, you see here the non-inferiority margin has to be set. That in this example we have set the difference in the AUC is 10%. So minimum that the difference has to be within 10%. Okay? Then I would say one test is as non-inferior to other tests. So how do you choose your margin? That is up to you. So you have to choose the margin. This is, say for an example here, this is the performance of two tests. You see here 86% AUC and the 80% AUC, the difference is 6%. Can I say yes, it is non-inferior? This one is non-inferior. Yes or no?
Yes.
Yes. What we need to do is, we need to find out the confidence interval for the difference. It so happened in this study, the difference is 6%. If the study gets repeated, I don't know, it may be 9% or 12%. The difference could be 12%. Okay? So therefore, that you need to establish the confidence interval of the difference and see whether the lower limit is within 10%. The lower limit of the confidence interval is within 10%. To conclude, one is this. Say for example, lower limit is how much here? 6%. Okay? I don't know, I'm not, this is, the lower limit is 6%. That is, within this, I think they have given the lower limit is 6%, which suggested that that is well within the 10% of non-inferiority margin. Therefore, you conclude that the second test is non-inferior to. Now, supposing this is 12%, this is 0.12, then I would conclude that this is inferior. Is that clear? So you need to establish the confidence interval for the difference of the two AUCs and take a conclusion. This is, we can do it manually, but it is better you use the software to do that. Okay? But this is not included in the diagnostic test software. But this is for your information. So the comparison is getting better and better. Okay? Now you bring in the concept of non-inferior into the ROC and do it. The next one is, this is what the graphs of the one which we are talking about. Adjusting for confounders and covariates. So I'm going to use Dr. Aladi Mohan, he's the head of medicine from Purturi University. So he sent a paper. This is about serum PCT in predicting bacteremia and mortality. So they have identified the best threshold. So, and then the paper was sent for evaluation. One of the reviewers asked the question, you need to adjust for the age and gender effect in the ROC. Okay? And the question is, should we adjust for it? If we don't adjust for it, what will happen? What do you mean by adjustment? In fact, you can do a regression analysis using ROC cutoff values. Therefore, that a reviewer wanted to know that you please, when you can do regression analysis using the ROC values, it will be better you adjust for age gender. Okay? So let's see here, this is a cutoff value for predicting bacteremia. That unadjusted analysis gives you 3.2 and adjusted analysis for age and gender gives you different cutoff values. And you see the area under the curves are different and so on. So if you look at the graphically, if you look at this, this is this is unadjusted graph, appears to be very good, but when you do the adjustment, this graph not so good. You see this. So the theory gets better and better. If you think that this should be done, okay? Many times it is not a randomized controlled trial or whatever. So therefore, it is possible that you should be able to adjust it. Now the same thing was done for mortality. When you see this adjustment, there's a big difference in the cutoff values. And so the area under the curve, not much of a difference. You see here the mortality curves. Okay. So these methods are available. We can contact statisticians to do this kind of analysis as you go ahead in diagnostic testing. Yes.
So for the age and gender adjustment, what was the conclusion?
No, this is that they wanted this adjusted analysis. The paper wanted adjusted cutoff values, adjust the AUCs for that serum PCT values.
Can be done by the.
How will this adjustment?
That is, it's again basically it's a regression method we do. We can do it.
So that can be done by the statistics with clinical method.
Yes.
Only pure statistics don't know how to.
No, we, as I said, we are on the process of updating that software which we gave it to you. We'll incorporate this. That will ask you which covariates to be adjusted for. Then we'll give you the adjusted AUC, adjusted values, etc.
If anyone not aware about, we need to adjust or not adjust, or look for all the histories.
Yes.
Then it's.
Yeah, it is difficult because it is. No, he was not able to do it. He is a very good person and he is very interested in doing other animals. So he was not able to do it, so we helped him to do it.
How to know that the adjusted ROC is significantly different from the original ROC?
We don't take a significant difference. In principle, it has been adjusted. It looks like there is a difference. So that is all.
For example, in the regression analysis, we don't include all the correlates, whichever is clinically important or whichever is statistically.
Yeah, in fact, we can do that. In fact, he is asking whether when you put the age, it doesn't make any difference in the ROC that we can in fact do it. So this is a regression analysis. So that is not the focus. Even if it is a small change or no change, because we just do it mechanically.
So when we do such adjusted analysis, are we saying that this current cutoff is independent of age and gender therefore?
Yes.
After adjustment.
Yes, after adjustment. So do you want to say anything?
And especially in the periodic.
The one thing that is important is to remember is there is nothing called statistically significant confounding. You understand? Confounding is like beauty is in the eye. You look at it and say, an adjustment, if there's a difference, can happen. When you adjust for a potential confounder and the odds ratio, whatever changes, you say, there was a confounder. I managed to get it. So you're closer to the hypothetical truth, number one. In the other side of that, you should remember, when you look at sensitivity specificity, one important rule is we are dealing with extremely strong association. Like, we are not talking about relatives of 1.2, 1.8. No, that is not a diagnostic there. Here, usually the relatives are 10 or more. So adjustment hardly makes a difference in such condition. So if you're worried, for every study I do, should I do adjustment? In general, not. That's why Jeyaseelan said, somebody read a paper, somebody wanted to. But if you look, adjustment didn't materially change the whole question. You still are pretty close to your cross line. Had you been away, close to the periphery, it wouldn't have made it much different. The rule of confounding and control is if you're close to, in a diagnostic scenario, let's people do this way. So, things like odds ratio of a smoking and lung cancer is 15. Okay? A diagnostic test like Vidal, the odds ratio if you do, it'll be 81. We're talking about a different game plan here. Diagnostically, the odd associations we look at are extremely strong. So if you wish, I will want what Dr. Jeyaseelan was trying to tell you. If you think there may be a confounding, you should know it. If you think you should adjust for it, there are methods available. But by and large, in most of the modern technique, we come with tests which are so, there's a biological basis for the test. You seldom require a confounder control. That's all. You don't say next time when you do a study, oh God, do I now adjust for it? By and large, you don't need to. In clinical use also, we don't think about it. If it's a good test, we'll know it.
ROC practical. Can you please open your yeah. Okay, I'll read it because it has to read it. Shall I show it to you, or do you want to open the file? If we can open the file, open the file.
On screen, then we can do it.
Is that okay? It's a very simple one. So this is mine is in the desktop, and this is the data, and read the sheet, check the data. This is your data. I have this test, this tool, this is the outcome, this is another tool, and this is another tool. So we have 3 tools or 3 tests to be compared. First of all, I need to do the ROC. This is the outcome. This is your outcome coded as 0 or 1. Okay. Now just go to the, as I said, that ROC comes under the validity procedure because you have the truth, you know the outcome which has happened. So ROC and ROC comparisons. So this is one of my tests, and this is another test, and this is another test, and this is my outcome, which is coded as 0 or 1. 1 is deceased and 0 is non-deceased. Just say calculate. So this is just the graph, and you press this one, that gives you the AUC, and this is the summary statistics, Uden index, and so on and so forth, and the values and coordinate for each test, and this is the comparison statistics, so between each test. So when you press export, so it exports all the details as one document. So that is all you need.